The context in which we will be using integration is the context of area. And the simplest area we'll be looking at is a constant. So if I have a constant, something that's varying as a function of time, and a constant amplitude A, this could have been a voltage, this could have been a current, so for now we'll just say it's a voltage. Then at any time t, this would be a rectangle, and the area would be height, which is A, into the length, which is t. So the area of this, which would be here, this would be A times t. So if I drew a second graph, which was the integral of v dt, so this is what is referred to as the area of v dt, or integral of v dt. So if this would be at is a straight line with a slope of a, which means the derivative at any point is a. So if I take it at the same point t, I would find that the height at this point is actually a times t. This is at, a times t. Now if I integrated this once more, again for the same time, then now I have a triangle, and this triangle that I have here has an area which is half base into height. So height is at and the base is t, so I have half into base into height, which is at, which is half at square. So this, when plotted, this, which would be okay, if we call this as at, which is a fair thing because this is at, then this would be actually the integral of a t dt, and this would actually look like a parabola, which means it's not linear, which means at time, for example, t is equal to 2, I would have had half at square, this expression. Half at square would have been half into 2 square, which is 2a. So this would have been 2a, but at a point, let's say 4, this is not going to be 4a, this is going to be half into 4 square, which is 16, half of 16 is 8. So 8 times t. And if we looked at any point here, let's say 8t, and we looked at the slope of that, so if we take a derivative of that, then the derivative of that would give you a point that corresponds to the same time in the previous curve, and the derivative of this curve at as a function of t would have given you this value, which is actually constant here. Yeah, so now that we've done Python, let's look at how we would see this in that. The example I'm taking in Python is of a falling object. So I'm basically using a constant acceleration of 9.8. It's meters per second square, but as I said, Python doesn't actually understand units. So I'm taking the same, well, I'm taking an A range which is 5 seconds, and I'm dividing that by 100,000 points, so each point is 0.05 milliseconds, so that is 1 to 100,000, one step, and multiplied by that. And I'm just making it constant, forget about it. All it says is for the full length of t, basically there is no dependence on x, so for all t basically make it 1, and then I multiply it with 9.8 and I make it into an array, so I can do all the manipulations and plotting that I have been doing. So in this I'm going to have 3 plots, so let's run this. So subplot is a way in which I can draw multiple plots, so I can look at them versus each other without their the vertical axis would make huge difference otherwise. So instead of plotting everything in one plot, just have them in separate plots. So here I'm basically integrating the acceleration, and the mathematical way to do that is to use the trapezoidal method. So this is using, never mind. So if you integrate it, and this is how you integrate it in Python, you you would get the straight line that we talked about. And if I integrate it again, then I get distance. And that's basically this curve that we see here. The scales are extremely different in the two cases. The scale is around, I mean, this very small and around 10. This scale is going to 50, and this scale is going to some 125 or so. And of course, shown up to 140. So if I look at the same picture again a little carefully, I can see that so this value is around 10, 9.8. So basically around 10, let's say. So if I take it over 5 seconds, and this entire area should be around 50, right? It's a rectangle. The height is around 10, and this is the y-axis, x-axis is around 5. So this should be around 50, which is what we see here. So this is around 50. The value here is around 50. And if I integrate this again, then the area of this triangle should be half of 50 into 5. So half of 50 is 25. So 25 into 5 is 125, which is the last value that we see here. It's 125. So that's basically the bare minimum we need to know for integration.